but the assignment was nucleophilic aromatic substitution.
Yes.
And this is like this. S-N-A-R.
AR.
And this AR means aromatic. It's not unimolecular, it's not bimolecular, it's aromatic. Okay? And what I told you was, you treat this with sodium hydroxide, source of a nucleophile, yes?
Yeah.
Source of a nucleophile, and what happens? Well,
Nothing.
for this one in particular, what happens?
Nothing. No
Nothing
reaction.
happens. If this is what you have, that won't react. It will, but at a very high temperatures, okay? It's a bad reaction, not so good. Okay, so since it normally doesn't happen, so this is not good. Now, this will happen if you do what? If you do what? Add a
A strong withdrawing? A strong withdrawing, right? Electron withdrawing.
electron withdrawing group.
Yeah.
I don't know how I'm going to remember that, to say the truth. For electrophilic aromatic substitution. For electrophilic aromatic substitution, we need the benzene ring to be what? Negative or positive?
Negative.
You need it to be negative. That's why the activators that you have on this benzene ring, they're all electron
Releasing.
Withdrawing
donating
or
or electron
donating.
releasing.
Okay.
Because we want the aromatic system here to have electrons to do the attack on the electrophile. So the good groups for this, or the groups that are called the activators, they all have some type of electron pairs there, okay? Or they are electron releasing. Now, there are two things. There are electron releasing or electron donating by resonance or by inductive effect, okay? There's different things. But I don't care too much about that. Now, here, what you need here is this thing to behave like what?
Electrophile.
You need this to be the electrophile,
Mm-hmm.
okay? You don't need this to be the one that is attacking something positive, so this needs to be very negative. This is getting attacked, so this needs to be positive.
Positive.
And in order for this to be positive, how would you take electron density away from this ring? By adding electron
Withdrawing group.
groups, like NO2. The electron withdraw.
So sorry.
I'm really trying.
Yeah, you can tell.
I left super far from here.
That's right, me too. But don't worry, I'm so rich I came in a helicopter. Okay, so we need this to be electron
Withdrawing.
withdrawing, so this ring could become.
Positive.
Now let's take a look. What sign is this?
Plus.
Hello?
Plus.
Positive.
How do you know?
Because the
Because
oxygen
it's
is
two oxygen.
That's why.
Because it's
Because
connected to
it's
one
one of
thing.
oxygen actually is making a double bond.
Because you know the Lewis S structure for this, and you know that the structure of this is like this.
Mm-hmm.
That's neutral, and this is
Positive.
plus. That's how you know. That's okay if you know, okay, element, electronegative element, that must be positive. No, this is a positive charge on this thing. Okay? So this is positive. That is going to be, you see, the charges have to jump from one side to the other.
Mm-hmm.
Okay, so if this is positive, that must be negative, and this must be
Positive.
positive, and this must be negative, and that must be positive. And that's what we want.
Oh, okay.
Because we want this negative charge to attack there.
Okay.
Yes or no?
Yes.
If this group were in the ortho position, if the group were here, that will be positive, this will be
Negative.
negative, that would be
Positive.
positive. If the group, so it's the same thing. So the electronegative elements need to be so far in what position? Ortho para. If the group were here, This would be positive, that would be negative, this would be positive, and that would be
Negative.
negative. Nothing is going to attack it there.
Okay.
Because electron density here is negative, you are not going to have another boy going here. It's not gonna happen.
Right.
Is that clear?
Yes.
So, for this, what's that called again?
Nucleophilic aromatic substitution.
Aromatic substitution. For nucleophilic aromatic substitution, the ring has to have an electron withdrawing group in the para position or in the
Ortho position.
Electron withdrawing groups that you should have are very electron withdrawing, very strong, which are
NO2.
CF3,
NO2.
NO2. Okay? How's that?
That's good.
Now the book sometimes says things that I don't like. Okay? Like they use the word install. I don't like it, okay? Install makes me feel like it's related to like
Cable.
mechanic work. You know, so I don't like to say install. I don't even know how to say it, but so what I want you to do now is guys, this is gonna be on the test. Any doubt about that?
No.
You lazy, know it.
On test number 2, right?
This is on this test, man. We're not finished with the stuff on this test. You're gonna have a full class today of weird looking things. I was trying to lubricate you before, okay? So now you get the real deal.
I was feeling relaxed over here. I think it's not.
Well, tense up a little. Yeah.
Are the rules do they apply for the Benzyne mechanism too?
What?
Do those rules apply for the Benzyne mechanism too?
Like aromatizers.
Is that the Benzyne mechanism is a little different because you don't need a group there.
You don't need a group,
You
right?
don't need a group, no. So, but when the rule applies, yeah, probably if you had something there, it could make attack on one side more than the other. But anyway, after you form the benzyne, then
Yeah.
you lose,
It reacts.
yeah, you lose that site. Okay, so what I want you to do is, you guys enjoy mechanisms, don't you?
We just love them.
Why don't you try that mechanism? Now, I was thinking of asking for this mechanism on the test without ever doing it. Because this is really related to what we have done, and I'm not gonna lie to you, I have done how many mechanisms? Like, I have done so many of them, I am disgusted by it. Like Agent Smith from The Matrix. You have 3 minutes.
That's what I
Okay, so here's what's gonna happen. Negative charge is going to attack yes? Now what? The VR is going to leave?
No, not yet.
It
They gotta go
will
all the way around.
at the
here.
end,
At the end.
at the
Yeah.
extreme end,
Uh-huh.
but it's not gonna happen at the first thing. And now I attack here, I make a new bond. What do I do with this pair of electrons here?
It goes to the carbon
It has to go
Go
somewhere.
somewhere.
Is it gonna go here or here?
here.
Only two chances or choices. You'll
Right
go
there.
there.
Yeah.
And what this is going to give you is say here's the VR. There is a new nucleophile. We're meditating this. You just want to have a happy Good morning, my friends. Okay, so negative charge is now here.
Yeah.
Yes? And now there must be a resonance to this.
Mm-hmm.
And the resonance will be, this electron pair will make a double bond there. And what's going to happen to the,
Negative charge
this double bond now is going to go where?
to there.
Right
It's
there.
going to go here. And
Uh-huh.
once again, the charge has moved. 1,
One,
2,
two,
3. It's just different from the previous charge. The previous charge was positive,
Mm-hmm.
and this one is
Negative.
negative. It's the same thing. Now this is the one doing the bonds, and before the double bond was the one going to the positive. Yes?
Yeah.
So this is different. If you have not been doing your work and you feel confused right about now, this is where you repent of all your sins. Because it's going downhill from now on, my friends. Where's the double bond now?
On the bottom.
Huh?
Right there.
Right there.
Where? Right there? I don't know where right there is. Here?
Here.
Okay, that's what you meant by right there. So,
Basically
and
double
this
bond.
is
Negative.
negatively charged here.
Yeah.
Now this structure is stabilized by
Resonance.
this nitrogen here
It's positive.
is positively
Positive.
charged,
Yeah.
and this negatively charged next to it is stabilizing.
So, Professor Garcia, I remember last class we had something like that, but at the tertiary it was less stable. But this time, because you have that nitrogen that's positive, that's stable.
Yeah, but the reason why it was less stable when it was tertiary and negative was because all of this was pushing electrons to more electrons.
Okay. All right.
So this nitrogen here is very electron deficient, yes?
Yes.
It's positively charged.
Right.
So this nitrogen is dying to get electrons, yes?
Mhm.
So whenever the electrons are nearby, it's taking electron density from it,
Oh,
it's
okay.
stabilizing.
Okay.
So now here is electron pair goes and makes a double bond there.
Mhm.
And now this one can't stay here, so this one will go there. You agree?
Yes.
So now here, and now it's about time to do what?
That leaving group gotta go.
Now we are going to say, okay, I am going to make a double bond here, and this bromine is going to leave, and it's going to regenerate the aromatic system. Yes or no?
Yes, sir.
The exam will be Thursday of next week, okay? It's not on Tuesday, so I give you time for you to study over the holiday. The holiday is not for you to go to the boat or to the beach. I am going to look for you at beaches and clubs. If I find you, you are failing my course. Okay?
Is that a reason for you to go out to the club?
It's for work, it's for work.
I am looking for you, so that's why I'm going out. It's not because I want to. All right. Now, let's say I were to give you something like this on the test, right? Your guess, right? Let's say I were to give you something like this on the test. And whether it happens or not is besides the point. Your guess would be what? What is this going to give you?
So add that.
OCH3.
It's gonna what? It's
Yeah,
going
those-
to that
Replace
or
that,
replace
yeah.
it. That is your guess, right?
Yeah.
That is your guess, and I am not going to tell you otherwise. This could be a nucleophile that does this, but if the base is very strong, okay? If the base is very strong, it is not going to be a substitution reaction. If the base is very strong, it is going to act like a base. You were copying it still?
Yes.
What's taking so long? You should have told me. Yeah, you're right. You should have told me. But it's okay, don't worry. It's
Just
okay.
record it.
Okay? So let's say that what I have is this. Let's say that that's what I have. And I treat this with a very strong base like this. Sodium amide. So this is a very strong base. What is this going to act like? It is going to act like a base. And it is going to pull a proton off. And it's going to do an elimination reaction. Okay? So, do you guys remember before how a base pulled the proton off and the Br left?
Right.
Yes, to form what? To form an alkene.
Yeah.
In some cases, you could have a double elimination in which it formed an alkyne.
Alkyne.
Here, this base can pull this proton off, or this one, yes? But let's pull this one off, because this one looked a little weird. So, we pull this one off. Okay, let's say pulled it off, and it will form. Pulls this off, and the Br leaves. And what that is going to form is a triple bond there. And this is called benzyne. And this reaction is called elimination, because what was it that happened first?
You pulled the proton off.
Pull the proton, elimination, addition. Now things can add to this triple bond here. What are the things that can add to it? This is in that and this. Huh?
Nucleophile, right?
Something has to attack it. Is that going to attack something? Or is something going to attack it?
Something's going to attack it.
Something could attack it. This can also participate in a Diels-Alder reaction. Yes?
Oh shit, yeah.
Hello?
Yeah. Yep. Wow.
Participate in a Diels-Alder reaction, but something can attack it. If something attacks it here, what's going to happen? Let's say that what attacks it there is I don't want to say NH3, but all right, whatever. Something attacks it there, what's going to happen? Now, these two electron pairs are going to go here, yes, to form this type of intermediate, will be positively charged, yes?
To the lone pairs.
With a negative charge,
Negative,
this negative
yeah.
charge now is gonna get a proton from somewhere, okay? Could be a proton from here, could be a proton from the solvent, and this will finally give you this reaction. And could it have attacked here? This, instead of attacking here, could it attack on this carbon?
Yes.
It's no difference. So it could either attack there or here. So let's say we follow this carbon here by writing this. One product could be the attack on that same carbon, and the other product could be the attack on the other carbon. Yes or no?
Yes.
Provide the products. Now, as far as you know, those conditions are they any electrophilic aromatic substitution? Are they electrophilic aromatic substitution?
No.
Hello?
No.
They're not
No.
electrophilic aromatic substitution. There's no electrophile there. There is a nucleophile,
Yeah.
but even better than a nucleophile, this is a very
Strong
base.
Yeah.
Whenever you have this base, what is going to happen is
Elimination.
elimination. Okay? That base will give you elimination. I'll never give you that base, and I expect you to tell me it's a substitution. The only substitution I'm going to ask you is nucleophilic substitution that is aromatic will only be with the OH minus. Okay? Possibly O minus CH3. So some type of alkoxide. So provide the product. What's the product? Here's the method. Where do I put the NH2?
On the top.
Like that? What would that be?
That would be,
Because it's
Uh-huh.
elimination.
That's good? Okay. So, we have another one in which,
NH2 is there because
It
we
would be
formed
here.
that triple bond already, right?
okay, so the triple bond formed either here,
Yeah.
no, not there. The triple bond either forms here or here.
Uh-huh.
So the attack can be here or here. So
Right.
it could be para to this or ortho.
Ortho to
I
that.
mean, not ortho.
No.
Meta.
Meta.
Okay, there it is, meta. I mean, it was
Ipso.
ortho to this one, but let's compare it to this one.
So,
So you get those two products.
okay.
So we always have to write like the two products, we just can't do one over.
If it's elimination.
because that's elimination, and that's the only example I give you, okay? I mean, the only example with this here, this and this will give you elimination when you have a benzene ring.
There's more though, right?
More what?
There's other strong base that can cause elimination too, right?
Yeah, but other strong bases will not be able to attack it. So, for you to have this addition afterwards, the base needs to have electrons of some sort. If you use an alkyl, if you use a base that is a carbonyl, after you form that base, there's no nucleophile that's going to attack that. So, let's talk about let's write a list about these activators and the strength. Okay? So, which ones are strong activators? Strong activators are those that are on the ring, and they are and they have electrons on the element next to it. The examples of these are like OH. And we're talking about the strong ones, okay? And O minus, of course. And the ones with nitrogens on it, because the nitrogen has that lone there.
So
Okay?
these are strong activators.
Those are strong activators. Yeah.
Can you repeat that again? What is the characteristics of a strong activator?
Strong are when it has this lone pair here that it could donate to this. Okay, those can do it very easily. The ones that are moderate, meaning not so strong, yes? They look like those, but they have something next to it. So if you have this with an R, this is less capable of donating those electrons. So this is a moderate group. I don't care for the reason, I care that you know which one are strong and moderate.
Okay.
And then if it has, what else can it have? Yeah, it could have something like that. Still electron pairs there, but it's not as strong as this because it's withdrawing electron density from it. Okay. What else could it be? Could be something with the nitrogen and that same idea. Okay? Those are moderate. Weak are those that have, where on R is where an R is a carbon chain, okay? This one here, I didn't write an R because they could be H's or they could be R's, okay? Doesn't matter. But if this is, an example of this is like a methyl group, yes? Yes or no? You should have known those from before, that should not be new to you. La Vista, did you know that from before? Okay, and now these are activators. They're what? They are ortho para directors. Am I missing any ortho para directors?
Yes, the chlorine, the halogen.
Yes, I am missing these ortho para directors. These ortho pair directors are halogens, or X is a halogen. The halogens F, Cl, Br, I. These are deactivators. And it is an exception to the activator orthopara directive. These are deactivators, and they are weak, and they are still orthopara. Yes or no? So we're still in deactivators, yes? So now moderate deactivators. Which ones are moderate deactivators?
That's so three.
Okay. All right. Why you choose this one? This is like an obscure thing. Okay. You can have that. So element and that, whether this has here a nitrogen or, so let's say this is with an R, and this can have an oxygen, or it could have a nitrogen. Those are still moderate deactivators. What else? Now, strong deactivators. Which are the strong ones? Strong ones are NO2s, because that is positively charged, yes? And another one that is very strong is another that is positively charged. So how many groups would it have?
Three.
Three.
4.
It has three, it'd be neutral.
Like
Oh,
four.
If it had three groups, it'll be here somewhere.
I mean,
It would be there somewhere. It has to have 4 groups in which that will become positively charged. What else?
CF3.
Like, let's say CX3. Yeah, CF3.
So if it's connected to something with like oxygen with 3 bonds, and that would be positively charged, and that would make it a deactivator.
Yeah, but that's not stable.
Yeah, that's-
I mean, maybe you can pronate that, but then weird things are gonna happen. But the nitrogen is happy like that. You can have that nitrogen without positive charge all its life.
Oh, okay.
Yeah.
So that's why I said that. Okay.
Okay. All right, guys, how do you like that? Fantastic?
The last one.
Hard to memorize?
I said more stuff.
No, you should have known this already. I just separated it into strong and moderate and weak.
Making
Before I
it
did.
easier, yeah.
Uh-huh.
Those are the last one is activator. Another
What do you mean?
deactivator. The last one.
This?
No, the other one.
This? Yeah. These, all the ones underneath this are deactivators. Weak, moderate, strong.
and then all those are orthopara directors.
Yes. All of these are orthopara directors, and below this line they are meta directors. So meta directors are in general, meta directors are deactivators, and they are deactivators because they are electron what? Withdrawing. send you some slides that I have from another class, see if you like them, okay? They're concise, they don't have everything, but they have at least everything that I have explained. Okay?
Good
What
to have
else?
flashcards for.
I have a question. On the last one, the CF3, is it strong because the F is actually pulling the electron away?
Yeah. That's extreme.
So it's more partially positive than normal. Okay.
So technically here you could put CX3 because it could be any of the
Yeah,
halogens.
CX3. This could be CX3, in which it's any halogens. But the one I'm gonna give you in general will be F3. All right. I'm gonna erase it. You guys ready?
Yep.
Gouch is not ready. Gouch is never ready, man. Okay, let's talk about these.
Probably have a question. Like the ones that are moderate, because I noticed the difference is that the electronegative is directly to the aromatics, unlike the one that is moderate here. You have the carbon directly to the aromatic. So can that be electron withdrawing sometimes? Like
Which one?
the moderate activators. Can they be
These?
electron withdrawing by resonance?
They are electron withdrawing by resonance. I forgot to put a group there. They are electron withdrawing by resonance. I mean by inductive effect. Because this oxygen is withdrawing electron density from there. But by resonance, it's giving it electron density.
Yeah.
So can it add up as both?
It is both.
Both, yeah.
But resonance is more important.
Oh,
So
Yeah.
resonance is always a stronger one.
oh, okay, that inductive. Oh.
Okay. We were doing electrophilic aromatic substitution. Let's talk about the bad things from it. When you have this, let's say you have this, provide the product. What's the product? You guys finished it so fast?
Be, same thing. No. Actually, yeah, right. It won't be
Like that?
Yeah.
Yeah.
Seal.
No, that's it.
So the first, the beer is gone.
Okay. Okay, my mistake, okay?
Okay, is that gonna
This comes from somebody?
Yes.
So it's beyond.
Okay, that was like.
Okay.
There's no VR attached into it.
No, that's called, what's that called? Friedel-Crafts.
Friedel-Crafts.
Alkylation.
Yep.
Puts an alkyl there. Now, the problem with this is that Friedel-Crafts alkylations are subject to rearrangement. And of course, the electrophile that you are going to form here is going to be that electrophile. Yes or no?
Yes.
And this electrophile is not very stable. This is why these reactions are a little slow. And I'm going to show you next because of that. Now what can happen is there is some type of shift. What shift do you expect? Here, you're not going to have a method shift. Okay, what you're going to have is a hydride shift. So there's going to be a hydride shift. And what this shift is going to form is this carbocation. Because that is secondary
More
and
stable.
this was
Primary.
primary. Okay? So you are going to have this as a product, and you're also going to have that as a product. So this is what you write down. Write it down. Write it down. When using primary alkyl halides in Friedel-Crafts alkylation, they will always rearrange. Of course, gouch is still in the first thing, right? Where are you at, gouch?
Halides, after halides, in, when using primary alkyl halides.
I don't know, you're confusing me. You are when using primary alkyl halides? Your gouch system.
Alkyl halides.
In a Friedel-Crafts alkylation, when using primary alkyl halides in a Friedel-Crafts alkylation, they will always rearrange. Provide the product. So what is it going to be?
You got
One, two,
Two,
three,
three,
four carbons. One, two, three, four carbons,
Yeah.
and it is also going to have the rearrangement, and the rearrangement will be to a secondary.
secondary. Uh-huh.
Okay, so this was primary. This will be secondary.
Secondary.
It will have a carbon to one side and two carbons to the other side.
Uh-huh.
Okay.
Does it matter? Does it matter if
If you put it on the other camera,
Excuse me?
I put it on the second part.
Okay, I see what you did.
Huh?
You could do the second part.
Excuse me? What do you mean? Isn't that the second carbon?
On the other one next to the
It
right.
looks like it's on the.
That's what I put it. Is that wrong or right?
1, 2, 3, 4. 1, 2, 3, 4.
Yeah.
You mean to say that that is different from this? Right? I mean, the carbocation and second carbon, yes? Bond to carbon 2. Yes? Carbon 2 has 1, 2, 3, 4. You wrote this on top?
No, they're
No,
on
at
the
the
other
bottom.
camera.
On which other one?
The one next to the right.
Slide your hand down.
Right there. That's what I put.
Is it a problem?
Same thing. Same thing.
So, what you drew was this.
No.
No, no.
No. Not even that. That's a twisted now.
Yeah.
That's twisted. That's not how I wrote it.
Like this. Go down.
Huh?
This is like the first gloss. Right here. The first gloss.
Here?
Yes,
Yeah,
they put it there.
But like this, yes?
Dry line down.
Yeah.
There we go, you got it.
Like
That
that.
one? Scary for a second.
Yeah. Bond to 1, 2, second carbon. Bond to, if it would have been here, same, 1, 2, second carbon. Then you got 4. Same, it doesn't matter how you draw it. I mean, you could have drawn this like that. So it's just going to be multiple choice, or you have to, no multiple choice.
He said, what? Is this
You're in
multiple
good
choice?
shape, man, don't worry. Not multiple choice. If you draw it like this, I give you credit, you're right. You don't have to draw it the way I want to draw it. As long as
That's
you're
why I
right.
think it was multiple choice or.
Yeah, I know. But there's people like making fun of everybody, man, don't worry. It's not personal.
That's okay, I mean.
All right, guys, so that's that. So whenever you are using primary alkyl halides, they will rearrange.
Range, yeah.
Secondary, tertiary alkyl halides, will they rearrange?
No, it doesn't need to.
Tertiary alkyl halides, will they rearrange?
No.
They're already rearranged, yes?
yeah.
They get rearranged from factory.
From factory.
So when I ask you this question on the test, I expect 2 answers for this, okay? You don't give me 2 answers, there goes your grade.
How would you formulate the question?
The question will be formulated like this. I don't formulate it.
You see, aluminum beer,
Okay?
Couch already know how to do this.
So let's say this. Okay. Now read what?
No reaction.
Okay, that doesn't say rearrange. Okay, so these are vinyl, are they vinyl halides, yes?
Yeah.
Vinyl halides. No reaction for that. There is, write this down, no Friedel-Crafts. If the Benzyne ring is moderate deactivated or strongly deactivated.
Is it deactivated? You don't have to write it.
That's so sweet, thank you.
I'm a sweet guy, but nobody can tell. No Friedel-Crafts. Or strongly deactivated. Yes? So if you have this, on the Benzyne ring, and you try to do Friedel-Crafts, what's going to happen?
No reaction.
No rearrangement, yes? No rearrangement. No reaction, whether it's alkylation or acylation. Okay.
Moderately or strongly deactivated.
Why doesn't it react?
Do you feel compelled to know the reason why everything?
Yes.
because God made it that way. Go ask him why. When you die, you're going to have that chance, okay? He will judge you by it. Okay? But I'm going to give you a hint, okay? Since you asked. Is the formation of a carbocation here an easy thing? No, it is not an easy thing. Because of that. Now, what is this doing? The deactivator is deactivating the ring, yes?
Yes.
Making it slower. And because this is slower, and that's difficult to form, it's not going to be a good reaction. If this reacted very fast, whenever you make some of this, what's going to happen? It will react with it. Right? Since it reacts slow, and that is slow, everybody's slow.
So it's not that it's not going to react, it's just so slow that it
Forms very little of it. I mean, some of us don't have 1,000 years to wait around. My time is running. The other reaction is, whenever you have this group, this is NH2, and these are like little details that I don't talk about before, right? You cannot do nitration for this ring, because you will also oxidize this, and what you are going to have is a mess. You hear, Sophia? Why? Because you're going to have a mess. So here is no nitration. Okay? Meaning that reaction is no good. Okay? Not yet, huh? Let's do a couple in which we have multiple groups on this thing, okay? Let's say here we are doing okay, what is the product to that? So these are conditions for electrophilic aromatic substitution, what? Bromination. Yes. And now here we have two groups, right? Now this is going to be a problem. Because this group is telling us that the new incoming group is going to go where?
So the ortho pair.
Ortho pair. So I am going to go like this. It's going to go ortho. Well, the pair is occupied. Yes?
Yeah.
Save me some trouble. And now this group is telling us that it will go where?
Meta.
It's going to go meta. So that's meta. Okay, so both of these groups are telling you they are going to go in the same position, which is ortho to this. Which one has a higher effect? The ones that are activators always have a larger effect than deactivators. So if you have ever a problem in which one is an activator and the other one is a deactivator, and they're in opposing places, choose the one that is an activator. So here, no problem. They are both in what position? Ortho. So here's the CH3. Here's the NO2. The next group is going to go here.
Here.
Where is that one going to go? Conditions for what?
Or activators.
Yeah, conditions for what?
Nitration.
Nitration. All right. What type of group is this?
Activator.
Activator.
Because
Donate.
What type of direct? Ortho pair. Arrow there, arrow here. Okay? And now what type of group is this? Ortho pair. One goes there, one goes here. Which one wins? I mean, you have a choice. You either put it here or here. Where are you going to put it? You are going to put it
activator.
next, or you are going to determine where it's going to go based on the strength.
Strength. Okay.
Which one is a stronger group, the OH or the CH3?
OH.
The OH is a stronger activator or deactivator?
Activator.
Activator. Wow. And I'm telling you, I'm in love with you guys. Since the first day. So this is which one? What do I put here?
NO2.
NO2.
Yep.
Very, very nice. Don't you like this? It's exciting. What is what? E plus, yeah. Where does it go?
Underneath the OH.
So this group says it is ortho pair. That ortho position is occupied. This pair position is also occupied. That would leave us with that position. Okay? We got to look at the rest of it. Now this is telling us what? Ortho pair. Yes. Here's ortho. Here's ortho as well. So this is coming from this group. Which one has a larger effect? This group or that group?
OH.
OH has a larger group, so we are going to eliminate this one. Okay, we eliminate it now because this one is strong. And now how about this one? This is what type of incoming group?
Meta.
This is meta. Yes, meta will be
Would be there.
here.
Yeah.
Okay, so two arrows are giving us this one here. And of course, the one is going to be that ortho to that OH. It is a strong activator anyway. So the electrophile is going to go there. Huh? What don't you get? What seems to be the problem? Because this group here, weak or strong? Okay, let's say this. We find the strongest of all these groups. Which one is the strongest one?
OH.
The strongest activator, yes? That will be the largest effect. Here's the OH. So the strongest to that OH is ortho pair. Here's ortho, there's pair. So this is the ortho that's going to take place. Of course, we looked at the rest of them. Yes?
Is there a point, Professor, when the deactivators?
Is there a what?
A point when the deactivators take preeminence over the activators, like if you want to choose where to put it? Like you
No.
consider, okay,
Not
all
over.
the time it's always there.
Yeah, activators always. do another one. You are going to love this one too. You don't like it when I do electrophile by itself, right? How about that one? What is it going to be?
Bromination.
It is bromination. Where is it going to go?
It's gonna go next to, it's gonna go next to.
It is going to be orthopara, yes?
Yeah.
Orthopara. This is an alkyl group, it's orthopara. Problem with this is, it's not going to go in the ortho position because the ortho position is hindered.
So it has to be opposite.
This
So it goes
is
meta.
too big. It will go to the
Meta.
para
Para.
position.
Oh, okay.
Okay. So the product will be here. So write this down.
Wow.
Para better than ortho. Because of steric hindrance, yes. I'm going to say this is steric
It's not. The only thing is back.
effect. Okay, steric effect.
Now, there was another group on the para position, does it react at all?
You want another group in the para position, you said?
Okay.
He provoked it.
Right?
He provoked it. This what you want?
But that one is.
There you go. You choose.
It's still gonna go. It's gonna go meta. It's gonna go meta. Because they're all meta.
By the way, guys, look, I'm not gonna tell you. I didn't finish this. This is preferred, yes? This is preferred. So this is a major product. But that doesn't mean that this one never happens. Okay? So this one is, it also happens. They're both of them happen, okay? But this is a minor product. Okay? Now, when you have electrophilic aromatic substitution, and I don't want you to know this, okay? When you have electrophilic aromatic substitution, and it's an ortho-pair directing group, you always get a little bit of meta, okay? Even though they're not ortho-pair, I mean, they're not meta-directing groups, you always get a little bit, because all reactions do happen. There's just slower,
Right.
okay? So, this is the major, that's the minor. What I care about is, most of the time you know it's going to go to what position? To the pair position first, okay? Because it's the furthest away. And the resonance will be the same after all. So what about this one? This is orthopara, but now the para, like he was saying, is blocked, yes? So what are we going to do? We can only put it in ortho position, yes? So we're going to put it in the ortho position to which one?
To the bottom.
Okay, we're not going to put it in this ortho position. We're not going to put it in this ortho because that's hindered, meaning the reaction will be slow. So you're going to put it ortho to the bottom one. Okay?
The bottom one is the meta position.
The bottom one is meta to the one on the top, but it is ortho to the one on the bottom. The one on the bottom is smaller.
Do you get another product for that, or is that it?
On the bottom, because
You could get, yeah, you could get a minor.
This is the mic, it would because of
This is minor, this is major. How is this going to look on the test? On the test, it's going to look two ways. I'm either going to ask you for the major, so you give me the major only. Or if I don't ask you for the major, then you give me both. Okay? if I say provide all the products and determine major or minor, then you have to do this, okay? Let's do another one. You don't have any other question you want the groups on? I imagine that either him or Sophia would have asked for this one. Right, Sophia?
I'm not the question, this is like, what's it?
So,
What if they had a bunch of metals?
I told you, I don't like it when you ask what if.
Okay, let's say.
Let's say what?
That there were metal groups everywhere. Oh, never mind.
No reaction, okay. So, what about this? This a problem, yes?
It would have to be ortho to that one. Or parallel to that one. Ortho there. That's parallel. But if you put it in the parallel position, it'll be too close to that hindered one. So it'll have to be ortho to that one.
So, what the deal is?
So it's gonna be at the bottom. It's gonna be at the bottom, that's what I'm saying.
This one tells
Because if
you,
you look at it this way,
tells you,
no,
Here?
that's too, yeah, right.
and here, right?
But then that's too close to the hindered,
Okay, this one tells you,
ortho para,
this one tells you,
There or
here,
uh-huh,
there.
or there.
or here,
Right.
and this one told you here too. Or,
That one tells you the other one too, yeah, that one. So, the less
So the
hindered
bottom. So the
is gonna be
bottom.
that way.
so, my question is it going to go here?
No,
No, it will never go there,
Never.
ever. Because now this is two hindered.
hindered, right.
So between two alkyl groups, this product will be very, very, very small amounts. That doesn't mean that it never happens.
Right.
That means that it's very, very, very small amounts.
Mhm.
Would that one happen?
Yes,
Yeah, but
but very
Because of
small
steric
amounts.
effects, that will be lower amount.
Yeah,
Would this one happen?
yes.
Yes.
That's the-
This would be the major product
Uh-huh.
because that is next to the
Le-
less
Less
hindered
hindered
group.
ones, yeah. So you would put all three, or no?
No, you would say this is major.
Uh-huh,
You would say this is minor, and you would say these are the probabilities of you getting an A in this class.
I see that so far.
Which is
TENC.
it doesn't.
okay, very little, okay? All right? I'm glad we got that one out of the way. What else can we do, my friends?
Retreat. Like you only down for like 15 minutes. So I'm going into that.
Let's say we have here an electrophile. What is an electrophile going to do?
Let's see.
Well, that
Let's see what's the bad. Both of them.
is gonna go to the,
It's not the color of the other two.
it's gonna go to this way. Either one of those two positions.
Power position.
Because you look at the
Power will be over there.
Where's it gonna go, guys?
Para.
it's gonna go up the right.
Para.
Okay, this one is gonna go, take it where?
Ortho para. Right there. That's
Ortho,
ortho.
ortho taken.
Yeah.
to that and to that. And this is going to take it where?
Go to opposite for that one. Opposite, the NO2. That one.
So you gotta tell me meta, ortho, what?
Meta.
Meta to this one, yes?
Yeah.
And meta is this one
Is that one.
or
Or that one.
this one?
Right.
So 2 and 2 arrows, yes? So does it go here? No, because of
Steric hindrance.
where does it go? It goes there. It is pair and it is also meta and not hindered.
I have a question.
I have a question too. Can it go opposite of NO2? Opposite.
It don't matter, so that,
You mean pair?
Yeah.
No. It can go pair to this, it's not ortho pair directed. And it cannot go to meta to that, this is not meta directed. This is like a total confusion of what I have been explaining. Okay? That's all right, okay? You will know it for the test or you will suffer the consequences.
Skip it.
Now, I don't know if you have noticed, guys, is there an easy topic on these 2 chapters?
No. Frost circle.
Cross circle is easy?
Yes.
Cross circles like idiots.
That's easy though.
Cross circle?
It's just drawing it, but I mean it's an easy concept.
Okay. I don't want you to make a mistake, okay? The exam is going to have everything. The exam is going to be long and hard. That's how you like it.
No, we like it short.
Okay.
Now you know how long.
The what?
The output wouldn't be the one that actually directs, not the,
Yeah, it doesn't matter, it's paired to that.
I know, coincidence, but if I were to see those two, wouldn't I go by that?
Yeah, but this is weak. This is not such a big deal anyway.
So if it wasn't that big, it would still go with parasite.
Yeah, still go pair, always pair.
Okay.
Activators better than deactivators, yes? If you had to choose, you always choose whichever one is stronger. All right. So let's say we do this, guys, and this is called fuming sulfuric acid, yes?
Fuming, yeah.
Yeah, fuming. And what does that give you?
SO3,
So this reaction is reversible. Okay? This reaction is reversible.
I saw that. I saw that somewhere.
If you use concentrated
Sulfation, desulfation, right?
sulfuric acid, you can cause this reaction to go reverse if you use dilute sulfuric acid. So if
That's
you
gonna
use
be
this,
SO3H.
if you have this and you use dilute H2SO4, what you get is that.
why did you get that?
You got that
Why
because
did you get that?
Because it's an equilibrium.
Okay, so it has to do with the rate determinants, like if it's like the rate.
Not really rate determining step. This can break again. You know, this can leave and then, because this SO3H is a good leaving group. So you can replace it. It's equilibrium, reaction at equilibrium. It goes back and forth, right?
Yeah.
And that's gonna happen for when you have this aldehydes and ketones and alcohols, yes? It is at equilibrium, yes? So you can have this enol in which the carbonyl is the preferred. And sometimes in solution you get one over another for cyclization. But don't worry guys, whatever. Let's do one more. This group can, since you can put it on and take it off, this group is sometimes used as, by the way, what type of directing group is that?
It's deactivator.
Type of directing group.
Might have it up.
Meta-directing group. So because of that, sometimes we can use this group to block a certain reaction in a place you don't want. So this group here, you can say that this can act as a blocking group. I mean, you get here late and leave early.
Outstanding.
It's horrible. All right, so let's say let's say I want this. Question here is, how do you make this?
How do you make
FeBr3.
Oh, okay. You have to go
BR,
combination.
FeBr3.
And bromination is going to take place in the ortho to the hinder side.
Oh, no, no, no.
That's-
When you do bromination here, bromination is going to go where mainly? It's going to go here mainly. Yeah, you're going to have a little bit of that, and you can say, yeah, I make both and I separate them. No, we're going to use a blocking group, yes. That is the use of this blocking group thing. So what we are going to do is, we are first going to do this reaction. SO3, H2SO4. The major product is going to go where?
Pair.
Pair. That's a major product. Yes or no?
Yes.
And now we are going to do the bromination. And where is it going to go?
Has to go ortho.
It should have gone,
Next to.
should have gone pair to this, yes?
Yeah.
Major product. Now it doesn't have that choice. It's
Yeah.
being blocked.
Blocked. Oh, okay.
Now, I don't want this here, but I can take it off. So it's gonna go ortho pair, right?
Mm-hmm.
So here's ortho, and it's gonna go what to this?
Yeah.
It's gonna go meta. Even though that reaction we said before, it was not very good, this one does not have a choice. So whatever amount is formed is gonna be this one. And now what am I going to do now?
And it.
I'm going to take this stuff out with dilute
H2SO4.
dilute acid, H2SO4. And what it's going to do is, it's going to give you that. So, that doesn't mean that that is the best reaction in the world, but tell me, if you were to get, if you do this reaction, this is not the major product. This would be the minor product. And you get the major product here, this. And this is 90% and that's 10%. But all of these reactions are 90%. What would you rather do? Would you rather do 90% 3 times or 10% once? How much overall is 90% 3 times?
3 9s are 27.
What happened?
27.
No,
How
not
much?
27, but 30.
30.
Okay? 90% the first time, you lost 10%. 90% the second time, you lost another 10%. And then another 10%, that's 70%. Better than 10%, yes?
Yes.
So, this is why some of these are used once in a while, because they give you more.
So from that, cutting
Guys, how much time do we have left?
to
20, 10 minutes.
So
FeBr3.
the answer for that is dilute H2SO4.
Can you go another?
The answer?
The answer for that
And
is
then go
The answer
opposite,
is
make it
this.
major? Okay.
The
So
answer,
you can't.
the answer to how do you go from there to there is all of that.
Okay.
all of that.
1 hour and 55.
Same amount.
You should be.
And it's frame the blank.
No, not fill in the blank. This is just write stuff down, no blank.
He's like,
They
what did
haven't
I sign
explained
up
to you how
for?
the test is going to
You
be?
blank, you
That's
fail.
my first time doing it.
Uh-oh.
You blank, you fail.
Guys, we did the reaction for reducing NO2? NO2 to NH2, did we do that one?
Yeah.
Hello? You did not see that? I remember we did this.
Yeah.
We did this.
Yeah.
Hello?
Yes.
Yeah, we did it.
Yeah, we
You
did
may
that.
not remember because you haven't studied. That's why. We did this. What they said?
That's a zinc.
That's a zinc.
Yeah.
That's a zinc.
That's a 7?
This is zinc. Okay?
That's don't do that on the test, please.
It doesn't matter how it looks like. You're supposed to know that's zinc and
That's true.
HCl.
Yep.
Okay? If you don't know, that's because you're not studying, which means you will fail my test next week. You know what? Yes, you can drop one. So, look here.
Who dropped the first?
This is zinc and HCl again, but now you need something else.
HG.
And this is HD. This is zinc amalgam. And it doesn't matter what it's called. And this would take you to where?
Carbon chain.
Okay? You'll take that oxygen out. This is not a regular reduction with sodium borohydride, lithium borohydride, yes? Lithium, those will give you what?
But you wait.
And erase this?
The last part.
Yes.
Crazy. We did this 10 minutes ago.
So how you call this?
Reaction.
Zinc,
They don't have a name. No. This is reduction. These are reduction conditions. What else? Oh, I think we did all of these before. We did it, right? We have NBS.
Yeah, we did that. Yeah.
We did this.
Yes. Yeah, we did that.
NBS, 1 bromine here. If I say excess, and I
Excess.
remember saying this,
Yeah.
excess is 3.
3. Yeah.
Yes? 3. What else? We did oxidation 2 of the chain, yes? Which is going to give you a
Carboxylic
carboxylic acid
acid.
at the
Yeah.
end?
Yeah. Yeah.
So it's pretty much done.
So was the handouts you made?
No, this is the guide that I wrote
Oh, okay.
with some examples to do on the board. Even I don't understand some of this stuff. Okay, let's do this problem. How much time we have left? You said 20 minutes?
I have no
We
idea.
have 9 minutes. My time says 2 minutes.
My watch doesn't work. It's just an accessory.
I watched the video from this morning.
Cold, huh? Heartless.
Guys, do this problem. I'm not, check, am I on that video now?
No.
I don't like to be on video. Believe me. I'm taking some mental hit for me to be shown in this video. So you better show up to the test knowing all. Look, let's make a deal. If the average of the class is less than 70, I'm not doing videos again.
Oh.
You said less than 70? That's
If the average of the class is less than 70, no more videos. So, get ready.
Watch the videos.
Hey, the videos that's the ticket, man.
By the way, look, guys, this is how fast you have to do this. Look, from here to here, I expect you to take, if I don't give you this, you know how long I expect you to do this on the test?
5 seconds.
3 seconds, that's right. You look and you know. It's just the time it takes for you to draw this thing.
do it fast.
Now, if you go, oh, zinc and HCl, what's that? No, you won't finish the test. So, what type of group is this? Directing group.
Ortho pair.
You see, you fat. What do you mean? What's that? An oxygen with another group?
That's
What type of group is it? Ortho, para, meta? Ortho-para. Ortho and para. And the ortho to that is taken care of. What is this? Meta.
This is taking.
This is a meta direct. Meta. Meta. And meta. We want this bromine to be where?
But it's gonna be.
On the less hindered carbon.
We want the bromine to go here.
Yeah.
This side happens to be more hindered. So because both groups are showing you this and it's less hindered, the incoming group is gonna go here. Bromine. Not good, I can't make this. Unless
You block it.
I block it. Damn right you block it. That has a name. A name? Blocker. That's right, SO3. H2SO4.
Blocker.
That's the blocker. How would you forget the blocker? I would say that's, oh man. Let's say SO3H like this, okay? And now what?
Elimination.
Bromination. And the bromination, since that group, that place is being blocked, which was the less hindered place, now we're going to put the bromine here. Because it had no choice, yeah?
Yep.
What next?
Desulfonation. Dilute H2SO4.
Okay, dilute H2SO4. Dilute acid, okay? Feel like that.
Nice.
Do not tell me this is not the best thing that has happened to you so far. You are going to be able to make drugs. You are going to do all of this in the kitchen of your house. Let's do 5 more, okay? It's an NH2, okay? I want you to synthesize that. What time is this class over? Now?
30 after.
In 3 minutes?
3 minutes.
Okay, you try to make this one and this one. I guess you're gonna do it in your house. I think that's all I wanted to do. Well, I wanted to do more, but
You want us to synthesize because we're starting from an empty Benzyne ring?
yeah, empty Benzyne ring, yeah. Question on the test is, this will be the last question on your exam, and it will look like this. Synthesize with anything you want. Well, you can't start, okay. Starting from here, okay? What do you mean you don't get it? Synthesize, man. Make that.
acceleration, Friedel-Crafts acceleration. One's gonna be like safety, then you gotta reduce it, and then one's
Guys, you have 1 week to learn everything very, very well, okay? I'm not playing with you. I'm gonna give you all the hard stuff on that test, okay? Including this, I won't put a lot of this because I expect most of you to get these questions wrong on the test. I'll put like 2 or 3.
How many questions are you usually going to say?
700.
80 questions?